The last video defined the notion of a presheaf F on a topological space X, which for any open set U in X gave us things which behave like functions on U. We call these the sections on U. And now the next step, or the next notion that we want to introduce, is that given really a point A inside X, we will consider a notion of stalk of F, which describes somehow possible functions on very small neighborhoods of this point A. And as a side remark, before we dive into this language, I wanted to point out that the language here is really very much inspired by kind of agricultural language, because a sheaf in English is one of these collections of stalks of wheat. And so I just want to point out all the language fits together nicely, and that's actually invented like this. Anyway, so somehow, just if you're wondering why we're calling these things with these strange names. Because essentially, I mean, to stay with this picture for one more second, is that the idea is that one of these sections of U, and this will also be an exercise, is basically determined by its behavior on these stalks, so by its behavior around each of the points A in the topological space. Okay, anyway, so let's go to the definition of stalks of presheaves. So if F is such a presheaf on X, and A is a point, then we define the stalk of F at A as a certain, first we define it as a set. So this F lower score A is, take the set of all pairs U comma phi, where U is an open subset of X containing A, and phi is a section of F on U, and we mod out by an equivalence relation. And the idea is, when are two such things equivalent? So you have one pair U and then a function section phi, and you have U prime and a section phi prime. And you want to say, when are those equivalent? And the idea is, well, the stalk should give you the behavior of the function in small neighborhoods of the point. And certainly, if we find some V inside X open, which still contains A, and which is contained in the intersection of these two things, with the property that phi restricted to this V is equal to phi prime restricted to V, then these two things should be the same in the stalk. And this is the equivalence relation, which we divide out. So in other words, if you want to compare two of the elements of the stalk, then you just need to check, do they agree on some, maybe very, very small open neighborhood of the point? And so mathematically, what you can check is that this tilde is really an equivalence relation, and that this quotient here is a K algebra. And so for this, you need to say, what does it mean to add, multiply two of these functions? And for example, if you want to add two of those things, then you're again given kind of one open set with one section, another open set with another section. A priori, you might say, well, I really don't know what the sum should be here, where only one of the things is defined. But that's not a problem, because you only need to define what the sum is on some possibly smaller open set. And so what you just do is you take the intersection of the two sets where the sections are defined, and then on there, you can really add them. And similarly for multiplication. And so here, this equivalence relation already comes in handy, because you can restrict to smaller sets, and this is used in the addition. And elements of this stalk are called the germs of the presheaf F at A. And just notation-wise, if we are really talking about X being an affine variety and F being OX, the sheaf of regular functions, then we write OX comma A for the stalk of OX at A. And we're going to see about the stalk a bit more. For now, let me make a couple of remarks. So first of all, these kind of germs of a sheaf F at A you should think of them as being section of F on arbitrarily small open neighborhoods of A. And sometimes for this reason, we also call these local sections of F at A, because they're really very localized around the point A. And let's see a couple of examples. So when X is the real numbers, and you have the sheaf, which associates an open set with the Euclidean topology to the ring of functions phi from U to R, which are differentiable, then, well, the stalk F at a point A, these are now differentiable functions which are defined on small open neighborhoods. And we say two of them are equivalent if there's an even smaller open neighborhood on which they coincide. And due to this condition, for example, we have some nice well-defined maps. We can take such an equivalence class and, for example, evaluate it at the point A. Because, well, if two things agree on some small open neighborhood of A, then of course they also agree at the exact point A. And so this gives you a well-defined map. And since we required the function to be differentiable, actually we can also compute the first derivative of phi at A. Because to compute the derivative, you just need a very small open neighborhood of the point to construct a limit defining this differential. And this is still good enough. So even if you restrict to a smaller one, this will not change the differential. And so this also gives you a well-defined map of sets. But on the other hand, once you have B not equal to A, even if B is very, very close to A, there's no well-defined evaluation map at B, because you could not guarantee that these open sets contain B. In general, there will be representatives here which do not contain B, and so it doesn't make sense to evaluate the function. So that's one thing. On the other hand, so this was with differentiable functions on the real numbers. But if you are, for example, look at the space X, the complex numbers, and then the sheaf which assigns each open set the set of holomorphic functions on U, then it is true that if you are given a section phi in this sheaf of holomorphic functions on the unit disk around the origin, then this section is uniquely determined by its germ at 0. And this is, again, this identity theorem, because once you know phi on any very small open but non-empty neighborhood of 0, then there is a unique function which can extend it like this. So in that case, we can extract a lot of information about the section phi just from its germ at 0. And kind of, at least in spirit, on affine varieties, regular functions are more in this direction here, as we're going to see. And at least one thing that we can do, similar to what we had before, when X is affine and A is a point, then we do have from this local ring of OX at A, we do have an evaluation map to K, which takes this germ of a function and evaluates it exactly at the point A. And as you can see, the next video will be about computing this here concretely.